A current I flows in an infinitely long wire with cross-section in the form of a semicircular ring of radius r. The magnitude of the magnetic induction along its axis is. Okay, now let us try to understand the situation. You have this semicircular cross section, okay, and current is coming out of it. This is a cross section of a ring, semicircular ring, out of which current I is coming, okay, and we have to find out the magnetic field at the center of the semicircular ring. Now this current I is spread across a perimeter, or you can say cross-sectional area, and that total perimeter of the area is pi into r, okay, where r is the radius and total current I is spread across it. So this is the current per unit length. So if I wish to find out what is the value of current that is flowing in this small element having length dx, then I can write current di flowing out of this equal to I by pi r into dx. Okay, now let us say you have a current element from which di current is flowing out of it, and this di element is at an angle phi with the radius, this radius, and the length of this current element, this angle that is made is d phi. Okay, so and this radius is r. So this length dl of the element, dl or dx, can be written as r d phi. If you substitute this value here, the value of current di will now become equal to I by pi r into r d phi, which gives the value of di as equal to I d phi by pi. Okay, now you have a current di, and if you wish to find out the magnetic field of this current element at a distance r, it will be in this direction, making an angle of 90 degree. Okay, this we already know. Now this current dB will be given by mu naught di by 2 pi r. Okay, so if I take the two extreme cases of a current element at this end and current element at this end, the magnetic field because of this end will be in this direction, and because of this it will be in this direction. Okay, and let us say this element is making angle phi or theta, then there is one more element corresponding to this element which is also at an angle theta having current di flowing through it, and their magnetic field would cancel out in the vertical direction. Okay, let us see in this diagram. So we get magnetic field spread across this for various elements. Okay, dB of different element, the magnetic field is different. Okay, so we know that if there are two magnetic fields dB and dB corresponding to same angle phi, then their vertical components will cancel out and horizontal components will add up. Okay, now what was the value of dB? dB was equal to mu naught di upon 2 pi r. Okay, now this can be further written into as mu naught di can be written as I d phi upon 2 pi square into r. Okay, now this magnetic field dB is making an angle phi. Okay, so if this is phi, then this angle is also phi, and the component of dB here and here, if we calculate, so dB in y direction will be given by dB cos phi, which is going to cancel out, and dBx is given by dB sin phi, which we need to integrate. So if we integrate this, we will get the magnetic field at the center. The total magnetic field at the center will be integral of dB sin phi, with the limits of phi being 0 to phi. Okay, now if we substitute the values of dB here, we will get mu naught I upon 2 pi square r as common, and sin phi d phi will be inside the integral sin phi d phi with limits 0 to phi. Now if we calculate this value, we will get mu naught I upon 2 pi square r. Now integral of sin phi is minus cos phi, and if we put the limits 0 to pi, we will get this value as 2. So we will have mu naught I upon 2 pi square r and 2. This 2 will cancel out. So we will get the total magnetic field at the center as mu naught I upon pi square r. Okay.